We are back for part two of heaps and priority queues. Going to be fun. What are we covering here? The heaps, right? Obviously, we're covering heaps. We're at part two of this. But what's really next? How are we going to build a heap? It turns out there's two ways we're going to look at doing this. One has a much faster improvement or performs much better than the first. How to implement a heap, the cool unique thing that we mentioned where we planted that seed, and then finally heap sort. The fact that we can use heaps to actually sort our data, super cool. So how do we build a heap from scratch? Let's assume here that we're just trying to build a max heap. So given an unsorted list of values, here are these values. How do we actually build our heap from these values? The answer is it's really just a series of insertions. We're going to insert at the next available spot that we showed you previously, and then we're going to simply percolate upwards if that insertion caused the heap to no longer be a heap. While there are more elements to be inserted, keep doing this again and again and again. Insert the next element, percolate up. Insert the next element, percolate up. Once we're done with the insertions, we have our heap. Let's go over here to the tablet. We have this written down, and let's just simply start. We have 54. That's going to be the root. And so now we simply want to insert the next node 87. Where does it go? It goes at the next available position, which is right here. Well, after we insert that 87, do we have a max heap anymore? We do not. So we need to percolate upwards until the 87 gets into its correct position. We need to swap the 54 and the 87. This is going to be a lot of erasing, but we'll go ahead and do that. This is now the 87, and this is the 54. Let's now insert the 27. Actually make this a bit wider. This will be the 27 here, and we'll insert this 54 way over here. 27, after we inserted that right here, it's a max heap. 27 is smaller than its parent. It is good to go. Let's now insert 67. We insert 67, and we see that 67 is greater than its parent. They need to swap. So we're going to swap 67 with 54. And do we need to swap 67 again? No, we don't, because it's now smaller than its parent. So I'm going to go ahead and erase that to make it a bit cleaner. And ultimately, we have here 67, and we have here 54. So now we want to insert 19. We insert 19 next. And when we insert 19, the max heap is still a max heap. We're good to go. We insert 31. When we insert 31, we see that we need to swap. So we're going to swap 31 and 27, and that's the only swap that is needed. So this becomes 31. This becomes 27. And now we need to insert 29. 29 inserts just fine. Next is 18 at the next level, at the very first position. We insert 18. Nothing needs to swap. It's perfect. We insert now 32. Thank goodness, not as much swapping there, but here we're going to have a big one. Next, we have 56. We insert. We insert 56. Actually, no, it's only one swap, but 56 and 19, they both need to swap. So let's put that in here. This is going to be 56, and this is going to be 19. Now we have 7. Oh, not there. 7 comes right here at the next spot. Then we have 12. 12 comes at the next spot. And apparently we have here, it says 31. Let's pretend it wasn't 31. Let's pretend it was 35. We insert 35 at the next spot. Let's pretend that was 35 up there. And when we insert 35, what's going to happen? It's going to swap right here with this 27, and we get 35, and we get 27. Let's actually insert now a larger value. Let's pretend we had one more value, 89. So when we insert 89 right here, what happens? Well, 89 and 29, they swap. So this becomes 89. But then we have to keep swapping. 89 and 39 and 31 swap. So this becomes 31. And then even 89 and 87 swap. So this becomes 89 at the root. Then we have here 87, then 31, then 29. So that's seeing it on the tab I'm going to very quickly click through it here on the slides. We insert 54, then 87, they then swap. We insert 27, no swaps needed. Insert 67, and now we have a problem. We have to make the swaps. Insert 19 next, it's solid. Now we insert the 31, we have a swap. We insert the 29, we're good. We insert next the 18, we're still good. Insert 32, good, and so on. So what is the running time of building a heap using that exact process that we just saw? Well, how long does it take to do one insertion? Pause the video. This is from last time. How long does it take to do one insertion? One insertion is O of log n, because you're going to insert at that lowest level, and then worst scenario, you have to percolate up or heapification upwards all the way until you reach the root. And since it's a complete tree, that height is guaranteed to be O of log n. So one insertion is O of log n. We have n insertions. So the running time to make a heap out of n elements is actually O of n times log n. For each of the n elements, you have a running time of log n to do the insertion. So we end up with n log n. But it turns out that we actually can do better than O of n log n time. What we're going to do is we're just going to place all of our nodes, all of our values into a complete tree in one go without doing any heapification. And just trust me, we haven't talked about how we implement this complete tree. We're going to get there, but pretend that we can just implement, and we don't need to do any traversing, that we can just implement this in a fast way where we can insert all of our values into a complete tree and at low, going by level, starting at the root and then simply going level by level by level. Then after we do that, we're going to, starting at the lowest level, we're going to perform percolate down commands, only if necessary. And we're going to work from the bottom and we're going to go up. But let me back up a little bit. Let me pause. Pretend one more time. We're going to have a tree that we're going to build how? By inserting all of the nodes or all of the values into this complete tree, but we're not going to do any percolation. So if we have 100 nodes, we're going to very quickly just throw in 100 things into this tree structure and pretend that the running time is O of n, because it is. So we can insert everything into this tree structure, this complete tree structure, in O of n time, and I'll show you how that's O of n. So now we haven't done any percolations, any heapifications, or whatever you want to call it. Everything's in this complete tree, but we don't have that max heap or min heap property. How do we get that? So we're going to work from the bottom and we're going to go up to the root, performing percolations if needed, performing a percolate down at every node only if necessary. And this process is called heapify or heapification. What is the running time? So I want you to realize that for a complete tree that is, let's say, 100% filled, even that lowest level, well, that lowest level has half of the nodes in your tree. If you have a tree that has 63 nodes, well, that last level has 32 of those nodes. You have a tree with 255 nodes, that lowest level actually has 128 of those 255. So for a tree that is completely filled, that lowest level has half of the nodes in that tree. What's the value of knowing that? Well, those half of those nodes, they don't need to percolate down at all because they're already at the lowest level. So think about this tree here. This is a tree with 31 nodes, 16 are at that lowest level. Well, those 16, they're already at the lowest level. So they don't have to percolate down at all. Now we want to look at the node above that. The level above the 16 nodes has 8 nodes. What can we say about these 8 nodes right here? We can say that if they're out of position, worst scenario, they need to do 1 percolate down. So how many nodes does this represent of your tree? If this last level was half of the nodes in the tree, what is this level? Just think about it. I mean, if this whole thing is half right here, then what is that last level of this portion of the tree? That's what is the number of nodes within that blue rectangle? In general, you might be counting, oh, there's 8. Okay, but in general, what does it really represent? The answer is it represents a quarter of the nodes of the tree. So a quarter of the nodes of this tree, at worst, will have to percolate down only one level. And then we can look at the level above that that has only 4 nodes right here. If these nodes are out of position, they're going to have to percolate down at most 2 levels. And then the level above that, those 2 nodes would have to percolate down at most 3 levels, and so on. So we can see that half of the nodes in the tree at the very bottom, they don't need to percolate at all, right? So I'm going to come down to the actual equation right here. So half of the nodes in the tree, they don't have to percolate down at all. Then a quarter of the nodes in the tree, at worst, each one has 1 swap. Then the next level above that, which is 1/8 of the nodes of the tree, at worst, those nodes have 2 swaps to get to the lowest level at their correct position, and so on. So if we can add all of that up, what is n over 2 times 0? Well, that's 0. Or what is 1 times n over 4, then plus 2 times n over 8, plus 3 times n over 16, plus 4 times n over 32. We're going to get this summation. What does it add to? It adds up to n. And here is the math. And we need to perfectly understand this math. I pause there. No, we do not need to perfectly understand that math. What we need to know is trust what happened, understand what happened, understand what we're really doing when we're trying to build this tree. I'm going to come back to here. When we had this tree, how do we get this tree of 31 nodes? We said we're just going to throw the nodes into that tree, the values into that tree, not in any order at all. So it's not a max heap, it's not a min heap. But now after we have these 31 nodes in there, we want to make it into a heap. So the running time to get the nodes into the tree itself was O of n. And I'm going to show you how. But now, how do we make this into a max heap or a min heap, given 31 nodes already in there in random spots? How do we make it into a max or min heap, or what's the running time? How we did it is how I just described. And the running time is as you see here. It turns out that if we have n nodes that are already in a complete tree, we can perform this heapification method or this heapification function, and it will run in O of n time. So long story short, what is the running time to create a heap out of n nodes? Well, we saw we could do 1 insertion at a time and then fix it each time. So we do n insertions. Each time we have to fix it, doing a percolate up, it's a log n, so n log n. Well, it turns out that we can actually do this in just O of n time by adding all n nodes directly into a complete tree and then performing this heapification process that we just saw. The major takeaway is, what is the running time to build a heap out of n nodes? O of n, with the understanding you're using heapification. Now we're getting to that super cool, super unique thing. How do we actually build our heap? I just said build our heap, like huge brain. We just talked about building our heap. How do we actually implement our heap? This is so, so unique and so cool. Remember, a binary heap is a complete binary tree. We can actually implement this complete binary tree as an array. Like, wait, what? And like, you can implement a complete binary tree as an array. Like, remove heap from the discussion, remove the min heap, max heap, the ordering property, the invariant, remove all of that. Just think about complete binary tree. You can implement a complete binary tree as an array. The question is how? Well, let's talk about it. If a tree is complete, we can simply say, let's put the root of that tree at index 1. Not index 0, index 1. Why? Because the math is easier. What math you'll see. But let's put the root at index 1. We're just not going to use index 0 of an array. So we have an array. We're not even going to touch index 0. Index 1 will be the root. The next two children, so the two children of the root, they go at index 2 and 3 of the array. Well, the four nodes at the next level, they go at index 4, 5, 6, and 7. And then the 8 nodes at the next level, they go at indices 8 through 15 and so on. Consider this tree here. The 5 goes at index 1. The 9 and the 11, they both go at index 2 and 3. Then the 14, 18, 19, 21, they go at the next four positions. And the next three go at the next three positions, 8, 9, and 10. That's really cool. So we want to implement, check this out, we want to implement one abstract data type. That is really the goal of all of this, these last two videos. We want to implement what? A priority queue. We talked about we could implement a priority queue using a linked list, sorted or not sorted. We could implement a priority queue using an array, sorted or not sorted. But ultimately, the best implementation of a priority queue is what? Using another abstract data type, a heap. So we want to implement a priority queue. And to implement that priority queue, we use a heap. What is a heap? This tree structure. It's a complete tree. It has this invariant where the greatest node will be at the top if it's a max heap and its kids will be smaller, right? We learn about this heap structure. But in the end, in order to implement this heap, which in turn implements the priority queue, guess what? We simply use an array. And it's how we dereference this array and manipulate the data within this array that makes the array a tree. So if I just give you an array of data and I tell you, hey, this array is a tree, you're like, okay, it doesn't look like a tree. It doesn't need to look like a tree. But if I give you an array and I say this array is a complete tree, well, then you know the roots at index 1. You know the next two values at index 2 and 3 are that next level. You know the next 4 values are that next level. The next 8 values are the next level, and so on. So we can really view that array as a tree, and it's how we dereference it. It's how we know what saves at each index that allows us to ultimately treat this array as a tree. So guess what? You almost like say all roads lead back to an array. Here we are back in our comfort zone, implementing a tree as an array. It's super cool. So we're going to store the data from these nodes into this partially filled array. So here the 42 goes where? It goes at index 1. We're not even going to talk about index 0. We know index 0 is there within an array, but we're not even going to touch it. And you're going to see because the math is easier by ignoring index 0. So the root goes at index 1. 35 and 23 go at the next two indices. 27 and 21 go at the next two, and so on. We're only concerned with the front portion of the array, the portion that has these values. And because it's a complete tree, that's what allows this to work. If this were not a complete tree and it had a hole, right, on level 0, 1, 2, 3, at level 3, where we were expecting 8 nodes, if there were only 6 nodes and we had a hole within that tree, well, that would be problematic because at that third level in the array, we need to see 8 values in order to guarantee that the next level will be the 16 values that are 8 over within that array. So here we have an example of a tree with 5 nodes being saved into this array. In the links between the trees, we no longer have this between the children, this left and right pointer, right? Their nodes are not stored using pointers and still, but it works as a tree, and we know which values are which within this array based on how we manipulate the array. So check this out. If we know the index of a given node, it's actually very easy to determine that node's left child, that node's right child. It's also easy to determine that node's parent. So before I even show you the equations, just look at this here. Let's look at 35 and 27. Well, 35 is stored where? It's at index 2. Where is index 27 stored? At index 4. So look at those indices, index 2, index 4, and try to ask yourself, well, is there some mathematical thing I can do to index 2 in order to get a 4? Or let's look at 42 and 35. 42 is at index 1, 35 is at index 2. What can you do with this index 1, with the actual index itself, 1, in order to get a 2? What can you do mathematically? And that same thing, if you do it to the 2, will you get a 4? And that same thing, if you do it to the 4, what will you get now? An 8, because check it out. This would be 1, 2, 3, index 4, index 5, index 6 would be here, index 7 would be here, index 8 would be the left child of 27. So, how do we actually make that happen? So, assume the name of our array is just A. The name of this array right here is just A. Check it out. The root will be at index 1. We already know that. The left child of any given node at index I, so I is now general, the left child of the node at index I will be found at index 2i. Check it out. Here we have node 35. It's at index 2. Where is the left child of 35? Guaranteed to be at index 4, 2 times 2. What if I tell you we have a node at index 11? Where is its left child? Guaranteed to be at index 22. Oh. We have a node at index 63. Where is its left child? If it exists, it's guaranteed to be at index 126, 63 times 2. What about the right child? The right child of a given node that is found at a particular index, the right child of that node at index I is at index 2i plus 1. So here, if we look at the 35, 35's right child is 21. Well, where's 35? 35 is at index 2. Well, let's do the math. If you take index 2, so 2 is your I, 2 times I, 2 times 2 is 4, plus 1 is 5. If we go to index 5, we should see the right child of 35, and indeed we do. So this is the math. It's not hard math. Just for any given index, the left child is at index 2 times that index. The right child can be found at index 2 times that index plus 1. What about the parent? The parent of a given index will be found using integer division at index I divided by 2. So where is the parent of 27? We'll take 27 to index, which is 4, divide it by 2. 4 divided by 2 is 2, and sure enough, that's where the 35 is. What about the 21? 21's parent is also 35. Well, the math works. Index 5 divided by 2, 5 divided by 2, you might be thinking 2.5, but integer division, get rid of the 0.5, strictly the 2, 21's parent is at 35, found at index 2. So index 5 divided by 2, index 2, and we see the 35 right there. Super cool. Another example. Here we have this tree. This tree, of course, I hope you see it can be formed into this array. The root goes here at index 1. The 10 and 12 are the next 2 values. 15, 17, 18, 23, the next 4 values. And the next level, the next 3 values. So consider node 17 that is highlighted. We would like to find the left child of 17. We would like to find the right child of 17 in the array. If it exists, you can see it doesn't exist. And we want to find the parent of 17. So 17's position in this array is at index 5. You can count 1, root starts at 1. 1, 2, 3, 4, 5. 17 is index 5. Well, if 17 has a left child, where is that left child found? At index 2i. So at index 5 times 2, which would be index 10. So here's index 5, 6, 7, 8, 9, 10. We come to 34. In fact, that is the left child. So we can see here that the left child, I'll come down, is at index 10, which is node 34. The right child of 17, if it exists, would be index 2i plus 1. So 2 times that index 5, which is 10, plus 1 would give you 11. So at index 11 is where we would find the right child of 17 right here. It doesn't exist, and that's how we know that we're at the end of this tree. And then finally, the parent of 17, take 17's index, which is index 5, divide it by 2, and you're going to get index 2. So 1, 2, and we get 10 is 17's parent. That is super cool. So we've now covered how to build a heap. We've seen two different ways of building the heap, right? The n log n way. We also saw the heapification way. And now we've seen how to actually implement a heap using just a basic array. Final thing, sorting using heaps. It turns out we can use heaps to actually help us sort. Think of how you would make that happen. How can we use a heap? Imagine you have tons of data in an array. Not tons, I'm going to give you an array with 1,000 values. And these values are not sorted. How can you use a heap to help you sort that data? What would be your exact algorithm to make that happen? I'm encouraging you here to pause the video briefly and see what you come up with. Again, you got an array, 1,000 items, and now you have a heap that you would like to use to help you sort that array. You can make another array. You can use a heap. You have this array of 1,000 items. How will a heap actually help you sort? Let's look at the solution. It's super cool, and it is called heap sort. So yes, we can use heaps to sort our data. This is the algorithm. Build a heap with all n values from that array. So we're going to take out 1,000 values from the array. Let's call it n. We're going to take out all n of them from the array. We're going to spit them into a heap. We're going to throw them into a heap, or we're going to throw them into a complete tree, and then we're going to build that heap using heapify. What's the cost? O of n. We're not going to use the n log n method. We're going to do the O of n method. We're going to throw all those values from the array into a complete tree. We're then going to heapify it, and we get a heap. Now, what do? We're going to extract that smallest value. Let's assume we want it to be sorted in ascending order. So we built a min heap. So we extracted that smallest value, and then when we extract that smallest value, we print it. If we just want to print, or maybe we store it into a different array, no problem. But we extract that smallest value. Well, the extraction's O of 1. Now we have to fix the heap after we extract it. What's the cost of fixing a heap? You have to do the deletion process, right? When we extract it, we delete. We then copy that lowest value up to the position of the root, and then we percolate downwards, or heapification downwards. Well, that cost for one deletion is log n. So what are we going to do? We're going to extract that first item. We're going to fix it. That's going to be a log n cost. But now we found the smallest item and we printed it, or we put it into an array, whatever the thing is. But that cost was log n. Well, then we do it again. We get the next smallest item, which is currently at the root. We extract it and we fix the heap. Now we have 998 items left in our heap, and we do it again. We take the next smallest, which is at the root. So because the smallest always ends up being at the root, we can perform this process of extracting the smallest, fixing that heap, which is log n at every time you do a deletion and extraction. You remove it, you delete it, you fix it. That's a log n cost. How many times do we do that? N times. So we have log n to fix one deletion. We're going to end up deleting from our heap n times. And so the total running time to delete n elements from a heap is n log n. What was the cost of building the heap? N. So we get O of n plus O of n log n with a final running time of O of n log n to build our heap. So in summary, what is the binary heap? It satisfies these two properties. The tree property, we have this heap property where it's either going to be a max heap or a min heap. We have the shape property, which it has to be a complete binary tree. To add elements to our heap, we just place it in the next spot. We percolate up through the height, which is going to be O of h, or O of log n. We then, to remove elements from our heap, we remove that root. We fix it at a cost of log n by deleting the root, taking that last element, putting it at the position of the root, percolating downwards as needed. That cost is log n. The purpose of a heap is what? To implement a priority queue. We use one abstract data type to implement another abstract data type. That's cool. That's nerdy. That's awesome. But in the end, we ultimately implement this heap just as an array. And we know our array is a tree, is a heap based on how we dereference it and how we choose to manipulate the data in that array. Was it marvelous? I don't know. Wishes is our demotivator today from despair.com. When you wish on a falling star, your dreams will come true. Unless it's really a meteor hurling towards the Earth, which will destroy all life, then you're pretty much hosed no matter what you wish for, unless you happen to wish for death by meteorite. Horrible. It's been fun. Leave a comment. Take care, everyone.